All right, let's go ahead and begin. Okay, open up worksheet 3.2 and look at number 3 and work in groups, however you want, and see if you can figure this one out, and then we'll check it. So it's cis 1 ethyl 2 isopropyl cyclohexane. Figure out which chair conformation will be the most stable and why.
You said worksheet 3.2?
Yeah, 3.2, number 3.
Okay.
Oh, yeah. Here you go. All right, let's take a look at this. Okay, if we have cis, what does that mean? Are they pointing in the same direction or opposite directions? Same. So which direction do we want them to point? Up. Okay. If you chose down, that's perfectly fine as long as they're both down. Okay, so they're at 1 and 2. So we're going to go up on number 1 right here. Is that axial or equatorial? Axial. And then number 2, I have isopropyl is up. How will that be? Equatorial up. So I have that as axial, that's equatorial. Now I'm going to ring flip it. Okay, my ethyl was an axial up. Now it's equatorial up. And then, let's see, isopropyl was a equatorial up. Now it's axial up. This is equatorial. This one's axial. So which one do you think is better? The first one, why? Yeah, the largest group is equatorial. So either one, we have to have one of the groups axial, right? So then we just have to choose which one then will benefit more from being equatorial. So this one, because the largest branch, we'll call it, is equatorial, which eliminates those 1,3 diaxial interactions. Any questions on that one? Yes. Yeah, if you drew it in the line form, that's fine. Okay, now look at this one. Now work in a group again with this one and draw the mechanistic steps. Draw the mechanism for this reaction. All right, let's start checking this. What is our first step called? Initiation. Okay, and what will that look like? Yeah, we'll have chlorine with chlorine. And then what do the arrows look like? Yeah, one to each chlorine. And what do I form? 2 Cl radicals. What's the next step called? Propagation 1. And what is that always in between? Like between? Yeah, radical plus non-radical. Okay, and what's our radical? Chlorine. What's our non-radical? That carbon group. And what is going to be taken off here? Hydrogen, where? This carbon right here, right? There's a hidden one. Okay, so chlorine's going to make a bond with what we said? Hydrogen. And then this extra electron will go where? Stay on the carbon. So these two form what? HCl, hydrochloric acid, and then here I just have a radical. What is the next step called? Prop 2. Okay, what is my radical here? The carbon group. And what's my non-radical? Yeah, ClCl, chlorine. This radical right here is going to make a bond with what? One of the chlorines. And then this electron will go where? The other chlorine. So what bond do I form? Carbon chlorine. And then a chlorine radical. Okay, and then what's our final step? Termination. And what is that between? 2 radicals. And give me 2 radicals. Chlorine, chlorine. Which forms chlorine. Okay, so make sure you can do that on your own for an exam. Oh, speaking of, so the homework system thing is down. It's been down for a few days, I think. They've sent me an email. It's supposed to be up by tomorrow. Let me know if it's not. Okay. As of right now, I'll give you a couple more days to do the homework. I can't put that into the homework until I can actually get into it. But just know you'll have a couple more days. And if it doesn't show up until next week, then I'll give you longer to do it, obviously. But as of right now, I'll give you, a couple more days. So instead of being due Monday, I'll just have it due Wednesday as of now. And if I need to change that again, I will based on, the program, whatever. Okay. Yes. Uh-huh. Uh-huh. That it came from the bond between hydrogen and carbon? You have a bond is made, that has 2 electrons in it, and so that's where it came from. Just one of the electrons from that bond. Okay, so that's pretty much what we went over yesterday. We focused mainly on the cyclohexane rings, you know, the axial equatorial, which one's better or worse. And then we looked at radical reactions. So now we're going to look at, we'll start at thermodynamics. All right, I did want to show you this really quick. So usually radicals are written with just 1 electron shown there, that lone electron. Know that they do have lone pairs around them, so you could show all those if you want. But usually, just to really emphasize this lone electron, that's the only one they'll show. But do know there are lone pairs around it. Okay, they're just insinuated. Usually, yeah. It really can be any one that has 1 less electron, like 1 less valence electron, but usually they're right there about to form the octet. Okay, so we've already kind of talked about K. This is KEQ, which is the same thing as Ka or Kb. What does A stand for? Acid. B stands for base, and then EQ is just equilibrium. Okay, but K is K. Okay, this is just being specific. So equilibrium is kind of when your reaction stops. Okay, when you can't make any more reactants or can't make any more product. Okay, so it's kind of at a standstill. So if I had a large K, okay, think of it in terms of Ka if you want. Did I make a lot of product or a lot of reactant? Product, okay? The larger the K value, the more product you made. So would you think that reaction is reactive or not very reactive? If you made product, what are you trying to make at the end? Product. Reactants was reacting together. Okay, so you're trying to produce a product, right? So if you made a lot of your product, then you were very reactive, okay? Your reactants were reactive because they made the product. Now, if you had a low K, a small one, then what did you have a lot of at the end? Reactants. So was that one very reactive? No, because that means they didn't really react, okay? So remember, the reactants are at the beginning because they're reacting, and then they produce a product, okay? And what you're always trying to make is the product, ideally, okay? So if you make a lot of it, you're reactive, you have a large K. If you don't, you have a small K, you're not very reactive. So what about this one right here? I have a K that's 1.1 times 10 to the 19th. What can you say about this? Is that large or small? Very large. There's 19 zeros past this number here, okay? You'll know it's small because you'll have a negative exponent. So this is really large. So is this reactive? Yes. And did I make a lot of product? Yes. The larger this number is, the more product you made. Okay, so K can give us an indication of the reactivity of a reaction. And so this is part of thermodynamics. Reactions always go to greater stability. So let's say at the end you made a lot of products. Well, that tells us that your products were more stable than your reactants. Okay? Whatever you make more of, that's the most stable. So if at the end there's a lot of reactants left, that means your reactant, your starting material, was a lot more stable than your product. Okay? So K also can tell you stability. Okay, large K, products are stable. Low K or small k, reactants are stable. Okay, so whichever one's favored, that's the one that's stable. Okay, then we can look at a number called delta G, which is Gibbs free energy. And this is really just the total energy in a reaction, essentially. All the energy added together is your Gibbs free energy. Okay? Now how this works is that if you have a negative delta G value, that means it's spontaneous, okay, or reactive. That's because you are releasing energy. So think of it, that's favorable. Versus if you have a positive delta G, this is called non-spontaneous, okay, or not very reactive. And that's because then you require energy to make your products, okay? None of us want to do anything, right? You know, we're lazy, just like reactions, okay? So the more energy we have to put into something, the more likely it's not going to go, okay? So a positive means you have to actually do work. You don't want to do that, so that's non-spontaneous, okay? A negative means you release work, okay? So basically work is done on you, and that's a negative number, which is spontaneous, which is favorable, okay? And you can calculate these. I'm not going to focus so much on calculating these, but understanding it. Okay? So a large K, will that go with a positive delta G or a negative delta G? Negative, the one that's favorable. Okay? So if we start writing this down, we have a large K. That means we have a negative delta G. And what's favored, products or reactants? What do you make more of? Products. And it's spontaneous or non-spontaneous? Spontaneous. Whereas if we have a small k, it's pretty much just the opposite. So now I get a positive delta G. The products, or actually reactants, are favored. And it's non-spontaneous. What does spontaneous mean? It's reactive. It'll happen on its own. You don't need any additional work put into it. Okay, and if you look at this formula here, I'll give you a second to write it down. If you look at this formula, do you see that K is in the formula? Okay? And then look right here. Do you see I have a negative sign right there? That's why the signs are opposite. So if I have a high positive K, you know, that's spontaneous and favorable. But if I have a negative delta G, that's spontaneous and favorable. And it's, again, because the negative in the formula there, you have the opposite signs. So if we come back over here to this number, okay, based on this K value, what would be the sign of delta G? Negative, right? So would that be spontaneous or non-spontaneous? Spontaneous. Okay, they're calculating it there. Okay, and then factors determining delta G. So I told you that delta G gives free energy. It's basically your total energy. The two most important energies that we look at in a reaction are called enthalpy and entropy. Enthalpy is delta H. And that's basically the energy it takes to make or break a bond. And usually we look at that in terms of like heat. Entropy, we've kind of talked about this one before. This one is the freedom of movement. Okay? So the more movement a molecule can have, the more favorable it is. So usually what you want a negative delta H, because delta H is very similar to delta G. I'll show you here in a minute. But you want a positive delta S, because we want to be able to move. And then over here, enthalpy, we want to release energy. Okay, so then they go on. Here's the formula here. So delta G equals delta H minus T delta S, T being temperature. But you can see here, it's the addition of delta H and delta S that make up delta G. Okay, so both enthalpy and entropy are important. Okay, so again, delta H, going back to redefine it, is the energy it takes to make and break bonds. So that is, like I told you, it's usually the heat or the temperature we're looking at here, released or absorbed. So in general chemistry, you looked at endothermic and exothermic. So exo, meaning something's released, okay? Heat is released. So do you think a reaction will be hotter or colder? Hotter, because you're releasing heat. And endothermic, it absorbs heat, okay? So what will it feel like to you? Colder. So exothermic is a negative delta H. That's when you release heat. That's favorable. Think of like an acid-base reaction. If you put hydrochloric acid and sodium hydroxide together in a beaker, it'll get really hot, okay? That's very exothermic. And then endothermic, that's going to get really cold, and that it takes energy to absorb energy. So that's a positive, which is unfavorable. So if we add over here, okay, so for delta H, if we have a large K, a negative delta G, products are favored and it's spontaneous, what do you think the sign of delta H is? Negative. Delta G and delta H will pretty much always have the same sign. There's a few exceptions there, but like 95% of the time, this will hold true. So then, would that be exothermic or endothermic? Exo. Then over here, if I have a positive delta G, then delta H will be positive. And that is endo or exo? Endo. So they all kind of go together, okay? They're related. It's just different ways of giving you the information. So K, really what that indicates is the amount of product you make, okay? And the stability of it. G, usually we're looking at energy. But if you see, you can convert these back and forth between each other, so really they're completely related. And delta H is specifically looking at the energy to make and break bonds. So they all are related information that's just slightly different in what it means. So this is total energy, if you want stability, and this one's the energy it took to make or break a bond. Okay, then we talked about entropy. This is, they say, the change in randomness, disorder, freedom of movement. I like to think of freedom of movement. To me, it explains things better. So if we're looking at a solid, liquid, or a gas, okay, which one do you think has more movement? The gas. Which one has the least movement? Solid. So which one has the most positive delta S? The gas, the one with the most movement. Okay, and it's the same thing with molecules. Okay, but what we find out, though, is entropy, though it is very important, is actually a really small number. Okay, so let's say delta H might be negative 1.2 times 10 to the 5th kilojoules per mole or something. and then entropy might be 12 or something like that. Okay? So think of it in terms of, let's say I have 1,000 minus 1. Okay? If I subtract 1 from 1,000, does it really change that number that much? No. Okay? So entropy is the same way. It's such a small number typically that you can actually take it out of the equation if you want just a quick estimate of delta H. You see it's often very small. So usually what we say is that delta G is equal to delta H. Now if you want to get really exact and get the exact total energy of everything involved, then you're going to put delta S in the calculation. But for the most part, just saying that delta G equals delta H is a very, very, very good estimate of the energy in a reaction. So then the main energy involved in the reaction is just, like I talked about before, is the energy to make and break bonds, which is really the definition of a reaction, right? A reaction, we're going to break bonds, and in turn, we're going to end up making new ones. These are called bond association energies. And what's nice, these are delta H's. There's actually large charts in textbooks. So you don't even have to do it experimentally anymore. I mean, occasionally you do if it's a new bond or something. But for the most part, they have these charts that say, if you are breaking a CH3 hydrogen bond and making a carbon-chlorine bond there instead, they have a chart. And so I'll show you. Let's look at this one here. So this is just a tiny chart, but there's like pages and pages and pages of numbers. So if we look at this reaction, this is one of the radical reactions we did earlier, yesterday actually. So you see here, overall, CH4 is going to react with Cl2, create a carbon-chlorine bond, and HCl. So these are the same reactions we've been doing. So here, on this carbon, how many hydrogens are in the product? So here I have 4 total, if you count the 3 plus 1. But over here, there's only 3. So do you see that I'm going to break one of the carbon-hydrogen bonds? Okay? So right here, you can look up, well, to break a CH3 hydrogen bond, that will take 435 kilojoules of energy. Okay? And then remember at the very beginning of the initiation, we break the chlorine-chlorine bond. So then you can look, well, how much energy does that take? And it's written here, 242. And then we look at the bonds that we made. So we made a HCl bond in our propagation step. That releases negative 431 kilojoules of energy. So anytime you make a bond that releases energy, that's favorable. And then anytime you break a bond, that takes energy. So it's a positive. Okay? Then we also made a carbon-chlorine bond, which released negative 351. So basically in a reaction, this is how they usually calculate it if it's not given to you. They look at all the bonds that you make, or all the bonds you make, all the bonds that you break, add up the energies, and total them. Okay? So I have 242 plus 435. This is all the bonds that were broken. That took 677 kilojoules of energy total. And then they went over here and they added these together, negative 431 and negative 351, and they have negative 782. Now from there, you just have to add these together here, and you get negative 105. Okay? So that is the total energy after you look at all the bonds that are broken and all the bonds that are formed, so the total energy of the reaction, and we get negative 105 kilojoules per mole. Okay? So it's a negative number. So was this total reaction exothermic or endothermic? Exo. So was this favorable or unfavorable? Favorable, spontaneous, non-spontaneous. Delta G sign will be, and K will be big, large, whatever adjective you want to use there. All right. So I just wanted to show you kind of how they get these numbers. So, you can get a number for delta H as negative 105 kilojoules per mole. And how they calculate that is, again, they look at these charts. Now, this is the exact numbers you need, just happen to be here, okay? But you're usually looking through these large charts, and you write down the numbers that you need to break all the bonds, and then the numbers to form all the bonds, add them together to your total energy, okay? Okay, so that is thermodynamics. You're looking at K, delta G, and delta H. And from all of those, you can see if a reaction is spontaneous, non-spontaneous, favorable, unfavorable, reactive, unreactive, endo-exothermic. All of those are thermodynamics. Kinetics is the rate of the reaction. How fast does the reaction go? You have your reactants and your products. How fast do your reactants turn into products? It's usually measured by time. Easy as that. Some are easier to measure than others. Some you can actually see it, like you'll have a color change. I think in general chemistry, if it worked correctly, you had the iodine clock reaction, and it should turn kind of a dark purplish color, okay? And at the time that it took for that to form was your rate. You can also look at sometimes like a solid will form, and as soon as that solid forms, you'll know sometimes you can't see anything, so you have to actually use experimentation and different instruments and stuff. Anyway, but basically, the time it takes for your reactants to turn into products, that is the rate, okay? And then from there, we can look at rate law. So let's look at that. So kinetics is just fancy for the rate of the reaction. And we always want to look at, well, how can we affect the rate of the reaction? How can we make it faster, okay? And that's really the study of kinetics, looking at the rate, and how can we make the rate faster, okay? So rate law looks at one aspect of it. It looks at concentration, all right? So here's our generic reaction right here. A, B turns into C, D, okay? Now we want to look at if I increase the concentration of A or B, will that change the rate of the reaction? Okay, so rate law looks at the effect of concentration on rate. Okay, that's the only purpose of rate law. Okay, then from there we get orders. Now these can only be done experimentally, and usually experimentally you'll get something. Actually, let me just pull up the lab instead of me making up data. That probably won't make sense. This is lab 6 or 7. I can't remember. We'll see. Here it is. Okay, so let me show you. Okay, great. Not that one. Page 174. Manual. 174. Now let me show you the data table in here. Almost there. Here it is. Okay, so you'll get a list of data like this. And this is similar to what you're going to get in your lab whenever you do it. You're going to get something like this. So do you see here, these are concentrations. Remember, concentration is molarity, moles per liter. Okay? So if you make it more concentrated, so think about salt water. Okay? So if I put, 10, so we always have 25 milliliters of water. Okay, that's constant. But in one of them, I put 5 grams of salt, and the other one, I put 10 grams of salt. Which one's more concentrated? The 10 grams, okay? So basically, which one did you put more of your solute in? Okay, so do you see right here? These are the numbers for the concentration. The higher the number, the higher the concentration. So here I have 0.01 and 0.02. So you see those are double in size there. And then 0.02, 0.04. Anyway, so that gives you the numbers for the concentration, and this gives you the rate right here. Okay? So we'll come back to this, because right now that won't make any more sense. Okay? So now let's go to order. That's how you're going to experimentally do this, is to determine the order is by looking at that chart. And we'll go back and do that. But now let's define order. Order is how the concentration actually affects the rate. Okay? So there's zero order. If something's zero order, it has no effect on the rate. It's zero. Okay? So I can, let's say A is zero order. If I quadruple the concentration of A, it doesn't matter. It's not going to affect the rate at all. You can put 400 million times more A in there, and it will have still no effect on the rate. Okay? So if concentration has zero effect on the rate, that's called zero order. Okay? The next one's called first order. And basically, whatever you do the concentration, the same thing will happen to the rate. So if I double the concentration of A, let's say, in its first order, then the rate will then double. If I quadruple the concentration of A, the rate will quadruple. Okay, so whatever I do to the concentration exactly happens to the rate. Does that make sense? So that's like mirrors each other. Zero order, nothing happens. First order, the same thing will happen. And then the next one, second order. And this will always raise it to the second power, essentially. So if I show you this one, if I have a A, and let's say I double it. Okay, so I put 2 times the amount. So if I want to figure out what happens to order, it's a second order. So what's 2 raised to the second? 4. Okay, so my rate will raise by a factor of 4. So if I double my concentration, my rate will quadruple. And then you can keep doing that. So if I put, I don't know, 3 times the amount of concentration. Okay, so this goes up by a factor of 3. 3 raised to the second power, 9. So now my rate is going to change by a factor of 9. Okay, do you see that? So it's always, whatever you do to the concentration, take that to the second power, that's what happens to the rate. Okay, so which one affects rate the most? Second order. So if you have, 4, or 3 reactants, one is first order, the other is second order, which would be the most important to increase the concentration? The second order, okay? So second order will affect the rate the most. Zero order will do nothing. First order is kind of in between. Okay, so that's what the orders mean. So now let's look at this data table. Again, this is going to be similar to what you'll do in lab, and see if we can figure out what the order is for each of these. Now you can't just look at this and determine. So if I have this reaction that looks like this, I have no idea what the order is going to be. Okay, I have no idea. You have to actually do an experiment to determine that. So if I come back over here, I conveniently did this experiment. Now let's look. So what you need to look at is where something is held constant. Okay, so I have NO and O2, and these are my reactants. Okay, I want to look at only the effect of NO. Okay, so that means I want to hold oxygen constant, where it doesn't move because I don't want it to affect anything else. So where does oxygen not change in its concentration? Which experiments? 1 and 2. Do you see it's held constant there? It doesn't change. Okay, so let's see what happens over here. What happens to the concentration here on experiment 1 and 2? It doubles. So let's see what happens to the rate over here on experiment 1 and 2. So 0.025 to 0.105. It's a factor of 4. Okay? So when this concentration doubled, this rate quadrupled. So what does that tell you about the order? Second order. Okay, now let's look at, we want to analyze oxygen. So what do we need to do to the NO, nitrogen oxide? Yeah, we want to see where it doesn't change. Where does it not change? Which experiments? 1 and 3. Do you see they're the same number? Okay, so now let's see what happens to oxygen at experiment 1 and 3. So I go from 0.02 to 0.04. So what does it do? Doubles. Now let's see what happens to the rate there. I go from 0.025 to 0.05. It doubles. So when this one doubles, the rate doubles. So that is first order. And if you see here, here is the full rate law. Okay? Do you see the exponents there? So it says NO is second order, just like we said. And oxygen is first order. So they don't have anything up there, no exponent, that means 1. Okay? So K is just your K constant, your rate constant, I mean. All right? So that's how you determine your order. So overall order is whenever you add them together. Okay? So the order here is second, the order there is first, and overall it would be third order. 2 plus 1, 3. Okay? So that makes sense how to do it? I'm showing you this so you can see how to do your lab. Okay? But that's what everything means in here. That's important to know what in the world you're doing. It's great, you know, you can calculate things, which is important. But, you know, if you have a number and you have no idea what the number means, then it's kind of pointless. Okay? So let's take a break, and then we'll look more at kinetics. All right, let's go ahead and start back up again. Okay, rate law. What effect are we looking at? Rate and what? Like concentration, how concentration affects the rate. Okay, zero order means what? No effect at all. First order, same effect. Second order, squared. Okay? And how do we determine the order? Not the overall, but how do we get this? Experimentally, right? We can't just look at a reaction and just know, okay? You have to experimentally do that. And so that's these exponents here. Those are your orders. And in the overall order, what do? Add them up. Okay? Then there's what's called activation energy, or we're looking at the Arrhenius equation. This equation, so if you think about what would affect the rate, one would be concentration. This one looks at temperature and activation energy. Temperature is literally just the temperature you run the reaction at. Activation energy is the energy it takes for the reaction to start. Okay? So that's what the Arrhenius equation looks at. Okay? So you see here, here's our temperature, here's our activation energy. Okay? So that's another equation you can look at. So let's think about what if we want the rate to be fast, okay? Do we want the activation energy to be small or large? Small. We want, if we could, zero activation energy, okay? And temperature, what do you think typically is the trend there? Higher the temperature, the more energetic, right? Think about boiling water. Is water more energetic whenever it's sitting there, at room temperature, or when it's boiling? Boiling. I mean, you can see it bubbling and everything else. When there's more energy in it, it's more reactive, okay? So typically we want a higher temperature and a lower activation energy. Okay, so you flew back. So this brings us into the whole point of defining everything, okay? We're going to be looking at what's called energy diagrams. And this, what it does, it brings together thermodynamics and kinetics, okay? So in terms of kinetics, this is basically the progress of the reaction, okay? This is energy. So what they're graphing is energy over time, really. Okay? So do you see here, my energy starts there, it goes up, and in this case, comes back down. Okay, so let's look at this. So if I have a low energy, does that mean it's probably more stable or more reactive? Stable. Okay, stability corresponds to low energy. So I have a stable product there. So what do you think the sign of delta G is? Stable product is favorable, so it's negative. Okay, and K would be a large K, and delta H would be negative. And overall, this reaction is spontaneous or non-spontaneous? Spontaneous. And if delta H is negative, is that endo or exothermic? Exo. So you could tell by looking at this graph all of that we just did. And what you look at is look at your reactants, which is the start of it, and your products. If your products are a lower energy, then you have all of the favorable conditions. Okay, that's your exothermic. So lower products, lower energy products is favorable. Okay, here, do you see this like energy hump you have to go over right there to get to the products? That is your activation energy. Okay, so you go from here to the energy maximum, that is activation energy. The top, that's called the transition state. The transition state is really this theoretical state that sort of, kind of, maybe exists. Okay? It's, let's say I have a bond between A and B. The transition state would be A and B starting to break and forming a new bond. So it hasn't actually broken or it hasn't actually made a new bond, but it's beginning to, if that kind of makes sense. So it's like the initiation of the reaction. So it's not really anything that we can prove exists, but we kind of know it does. Okay? So that's the transition state. It's always at an energy maximum there. And then since we're measuring energy, if you take the height from the reactants to the products, you see like the height difference, that is your delta H. Okay, so there's numbers over here, you could actually calculate it. All right, now let's look at another one. We'll go over that in a minute. Here's a good one. First, this is the 2 energy. So if we go, let's just look from here, our reactants, all the way to our products over here. So overall, would you say this is favorable or unfavorable? Favorable, because our products are lower energy, so that's where we have the negative delta H, negative delta G. And if we can look here, if you look at the difference in the height, that gives you delta H. Okay? Now let's look at just one part of the reaction. Let's look at from here to right there. Okay? Now let's pretend these are your products. So is that favorable or unfavorable, that step? Unfavorable. Okay? So that's not spontaneous. You're going to have a low K, positive delta G, positive delta H. And you can see the height difference there. And you see I have a positive delta H number. Now, where are my transition states? Where are they located? At the top. And how many transition states do I have on this overall? 2. I have 1, 2. So I have 2 transition states. And then the one little part right here, kind of like the valley in between, that's called your intermediate. Okay? Intermediates do actually exist, so it's not like transition states, which are theoretical. So right here, for example, this is the intermediate they're looking at, this CH3 radical. So in the end, in our final product, you know, we had our overall reaction, our radical reaction. Did we have a carbon radical at the very end in our product? No. If I bring this up here, if we're looking overall, is there a carbon radical in this product? No. But did I have a carbon radical somewhere in these steps? Yes. So that's an intermediate. It does exist, but it's not actually part of your product. Okay? You have to form it to form the product, but it's not actually a product. So that's what an intermediate is. It's something that does exist, but not in your product. It's just somewhere in your mechanism. Okay, so be able to interpret these. Tell me what they mean. You know, I could ask you, give you this graph, and say overall, would you have a large K, small K? Is it spontaneous, non-spontaneous? What's the sign of delta H, delta G? Endoexothermic, all those kind of things. And I can actually have you label it, label the 2 transition states. Where's the intermediate? Or the intermediate is your valley. Where are the reactants and products on this? So reactants over here, products are always at the end. Okay. Label delta H. So delta H's are always your height differences. So be able to label those and kind of interpret what they mean. Okay, so then they go back to radical reactions a little bit. So when we were doing all our radical reactions, which halogen did we always use? Chlorine. Okay? And we didn't really use the other ones, and this is why. If we look at fluorine, if we look at the rate of it, so here's the rate of chlorine. Okay? 1,300 moles per energy or whatever. So here, 1,300. Fluorine, do you see I have 140,000? So it's a lot higher. Basically, what they found with fluorine, it's so reactive, it's actually explosive. Okay? So that's why we never use fluorine in the reaction. Then we look down here at bromine. So this is like your K. Think of it as that. Okay? So it's a large K. This is even larger K. Now look at this one, 9 times 10 to the negative 8 for bromine. Is that a large? No, it's a small K. And then down here at iodine, 2 times 10 to the negative 19. It's also a small. This one's the smallest. Iodine pretty much doesn't even react, okay? You would be sitting there for years waiting for iodine to make a product. Bromine, it's not that reactive, but they found that if you put like heat into it a little bit, it's then reactive. So if I have to put energy into something to make it react, would that be a favorable, or is that spontaneous or non-spontaneous? Non-spontaneous, because I have to put more energy into it. So bromine is non-spontaneous. So you see the K is small, so then delta H would be what sign? Positive. And delta G would be positive. And then chlorine here, we do have a large K. So is this one spontaneous or non-spontaneous? Spontaneous. So you can see. So that's why typically when we do these reactions, we put chlorine in there, because that's the easiest one to do. Occasionally you'll see bromine, because you can do bromine if you put a little heat into it, but usually we see chlorine. So then they further analyze this. Okay, so that's what we just said there. Okay, then they're comparing, for a few slides, chlorine to bromine. Okay, looking at thermodynamics, kinetics, and everything else. Okay? Here they're looking at chlorine. Now let's look at this reaction right here. Now this has, let me also explain to this, primary, secondary, tertiary. Almost forgot about that. Okay, a primary carbon means it's bonded to one other carbon. Okay, do you see this CH3 right there? How many bonds to a carbon does it have? Directly, 1. That's called a primary carbon. A secondary carbon has 2 carbon bonds. So do you see the CH2 right here? Do you see it's bonded to a methyl and a methyl? So it's secondary. Tertiary then is bonded to 3. So they don't have a tertiary on here, but it would be bonded to 3 carbons. This is sort of one here. The R groups stand for carbon groups. So you see a carbon bonded to 3 other carbons. And then quaternary would be bonded to 4. They had it on there. Okay, so primary, secondary, tertiary, that all deals with how many carbon bonds do you have. Okay, so here they're looking at a primary. So that means it's bonded to 1 carbon. And they're looking at the radical reaction. Here they're looking at taking off the hydrogen. So you know in the first propagation step, we take a hydrogen off. Okay? And now they're going to take it off a primary carbon. So a carbon at the end, like a methyl. And they found that the relative reactivity per hydrogen is only 6.67%. So not very reactive. It's not favorable. So then they look at the same thing. They're like, well, what about a secondary hydrogen or carbon? So putting it on the central carbon, and they found that it's at 30% per hydrogen. So a lot more reactive. And they calculated here it's 4.5 times more reactive. So we have to look at, remember when I did the reactions, if I even point out, here's what we did here. Chlorine is on what type of carbon? Right? It's only based off carbon bonds. So I'm looking right here. This dot, how many carbons are bonded off of there? 1, 2, 3. Okay? We don't count chlorine and we don't count hydrogen. It's only carbon. So there's 3 carbon bonds coming off of there. So what type of carbon is that? Tertiary. Okay? You're going to find that tertiary is even more stable or more preferred for your halogens to form there. So overall, if I give you the order, primary is the least favored, okay? You don't typically make your radical on a primary carbon. And that's the carbon where your chlorine is. Okay? Then, secondary. Then finally, tertiary. So they did this experimentally to see that. And the reason is, okay, let's say I have this radical right here, what would this be, a primary, secondary, or tertiary? Primary. So look at this carbon, and how many carbons is it bonded to? 1. So this is a primary. Now what happens here, methyls, or any carbon group, has electron density, a decently large electron density, at least compared to hydrogen. And what it can do is basically move itself closer to this carbon. So this carbon's electron deficient right now. Count how many total electrons are around it, this carbon. 1, 2, 3, 4, 5, 6, 7. How many do we want? 8. So it's electron deficient, meaning it doesn't have enough electrons. Okay? So what this methyl can do, hydrogens cannot do this, only carbon, or I should say non-hydrogens can do this, is that it'll move its electron density closer to that carbon, stabilizing it. So it kind of shares its electron density with that carbon, so it's not as reactive. Now let's look at a secondary. So I'm just going to use methyls right now. Okay? Now how many carbon groups can be used to stabilize this reactive carbon? 2. Can move closer. That one can move closer. Now if I have tertiary, how many do I have? 3. Okay? So that's why tertiary is always the most stable, then secondary and primary. And I know you can't see your homework right now, but it has questions pertaining to that. So it'll have a structure, maybe I don't know, like this. And you have to figure out what is the most likely position basically the reaction will take place. So where are you going to add your chlorine or your radical is going to form? So then you look at, what you do is look at your carbons. What type of carbon is that? Like primary, secondary, tertiary? Primary. Here. Secondary. So just basically count the lines coming off of that point. Here. Tertiary. Here. Primary. Here. Secondary. Those are all primary. And then the central one, how many do I have coming up here? 4. So it's called quaternary. Notice I didn't put quaternary on there. Okay, in propagation 1, we take off a hydrogen. Is there any hidden hydrogen right here? No. So the reaction can't even take place there. Okay? So that's why I don't even talk about quaternary. So looking at all of these, what's the most likely position the reaction will take place? The tertiary right here. Okay, so it's you trying to figure that out. And again, that's just because it's stabilized by all the carbons around it. Okay, so this is with chlorine, and we saw that a secondary is more favorable than a primary. It's 4.5 times more favorable. Okay, then they did the same analysis. Not here. This is just to show you the energies. Okay. Where did they do it? We talked about that. Okay. Here's where it is. So then they did the experiment kind of looking at chlorine versus bromine. Okay? So chlorine, that's the one we typically use. And was that one, do you remember? Well, here's the graph for it. So my reactants are up here and my products are down here. So is that spontaneous or non-spontaneous? Spontaneous. Okay? So it's everything about it is favorable. So what they did here, you see there's a green line and a blue line. Okay? The blue line is the energy diagram if you used a primary carbon for the reaction. The green line is a secondary carbon. Okay? Which one's more favorable, primary or secondary? secondary, okay? Now, when we're looking at activation energy, do you want a high activation energy or a low one? Low. So between the blue and the green, which one has a lower activation energy? The green. You can see right here. It's a lower energy hump. The difference, it says there, it's about 4 kilojoules, okay? And then overall, do you see it forms even a more stable product right there with the secondary, okay? Now let's go look at the bromine. So keep this in mind, okay? Okay, now here's where they do it. They compared primary and secondary carbons here. So remember, for chlorine, the secondary carbon was 4.5 times more favorable. Now they did the same one for bromine, the same kind of experiment here, and they found that it's actually 97 times more favorable for the secondary. So let's look at the graph so we can see this. Okay, so looking at this, would you say this is spontaneous or non-spontaneous? For non-spontaneous, so let's put energy into it. So this is bromine, and I already told you had to heat it up for the reaction to go. But look here. Here's the big thing. This energy here, the activation energy for the secondary, the green one, compared to the primary one. Do you see this difference here? It's over twice the difference. This is 9 kilojoules. The other one was 4. The difference there of energy. So it takes basically a lot more energy to break that primary or to make a primary bond there than it is for a secondary, especially with bromine. Okay? Now think of it this way. The energy it takes to break, or not really break, let's think of it, the energy to make a carbon-chlorine bond, will that be the same as the energy to make a carbon-bromine bond? No, they're different because they're different atoms. And you can see here, let me actually, there's a slide, there it is, that shows both of them on the same page. Okay? Now, carbon and chlorine, now typically you would predict, at least I would, that they'll probably react in a similar fashion. Okay? If we have almost the same reaction, the only difference is, are we going to use chlorine versus bromine? I'd predict it would be pretty much the same result. Maybe slightly different, but very close. But if you look at these graphs here, are they the same or even close to the same? No. One of them is endothermic. The other one is exothermic. Okay? One's favorable. The other's not. One's spontaneous. The other one is not. So sometimes you have to, the point of the story is to experimentally do these reactions to know. Okay? Anyway, and the big difference just came from making and breaking that chlorine versus bromine bond there. All right, then, what time is it? Okay. Haymann's postulate. So it's the last thing we need to know about the reaction diagram is Haymann's postulate. Remember I told you the transition state is this sort of theoretical, whatever, chemistry thing made up, whatever. Okay? Well, if we want to predict what it kind of looks like or most likely going to look like, that's Haymann's postulate. And what you do you see, for example, right here, here's a transition state, right? It's always at an energy maximum. Now, in terms of energy, is it closer to energy to the product or the reactant? Product. Just literally look at the height. Okay? It's closer energy to product. So that means it's going to look more like the product. Okay, so we call it product-like. Now over here, this transition state, is that closer to the reactant or the product? The reactant, so that one's reactant-like. Okay? Here's a good picture to show this. So we said this one is closer to products, right? So it's product-like. So here's our hypothetical transition state. So our product would be making HBr, okay? So it'd be making this bond and breaking that bond. So do you see that my hydrogen is closer to making the product? Meaning it's closer to forming the final product at the end, okay? Now remember, transition states are theoretical, so that's why we have the dots and lines in between, because it's not actually fully made that product yet. But if we stopped at that point in time, it's going to be closer to making the product. Now over here, this one's reactant-like. So do you see now the hydrogen is actually closer to the carbon, meaning it's closer to looking like the reactant. Okay? And that's all it means. Are you closer to breaking the bond right here? Or making the, or wait. No, because this would be making and breaking. So are you closer to forming the reactant bond or forming the product bond? Okay? So that's all it means. It's just you're trying to have some sort of idea of what the transition state looks like. Okay? And you literally just look at it and see, is it closer to the reactant or is it closer to the product? And that will give you an idea of what it looks like. It could also come up, let me go to that graph where we had a couple transition states somewhere. There it was. Okay, right here. Now, in this case, our choices can be reactants, product, or intermediate. Okay? So let's look at this first transition state. Is it closer in energy to the intermediate or to the reactant? Always look what's on each side of it. Okay? So which one? Intermediate. So we say that's intermediate-like. So we know our transition state. If we want to know kind of what it'll look like, it'll look similar to the intermediate. Okay? Now, what about this one right here? Is it intermediate-like or product-like? Intermediate-like. Okay? So we know that transition state will also look like our intermediate. Okay? Come back over here. Okay, so we already looked at, we're almost done with this chapter, and I'll let you go, I promise. Okay? I know we're all getting tired. So free radicals, we looked at radicals. Which one is the most stable, primary, secondary, or tertiary? Tertiary. Which one's the least stable? Primary. Okay, so if I had what's called a carbocation, what do you think a carbocation is, first of all? What's a cation? Positive charge. Carbo, what do you think that stands for? Carbon. So it's a carbon with a positive charge. So I have carbon, positive charge. So I have a methyl there, a hydrogen, a hydrogen. So that's my carbocation. Okay? Count all of the electrons around it. There's no lone pairs on there. How many do you count? 6. 1, 2, 3, 4, 5, 6. Right? Does it have all the electrons it wants or needs? No. So this is also electron deficient. You can see it has a positive charge. So it definitely wants more electrons around it. So do you think this electron density can stabilize that positive charge? Yes. Just like it with the radical. Anytime you're electron deficient, you don't have enough electrons, you want to stabilize it with electron density. So this one can stabilize it how many times? 1 with this one methyl. And if I had, let's say, a tertiary, how many times can I stabilize it? 3 times. So just like the radical, what's the most reactive, or most stable, I should say, for the carbocation? Tertiary. So it has the same trend. Now let's look at this one last one. What if I had this? Okay. Now count all the electrons around it. 8. So is it electron deficient? No. And then what sign do I have there? Negative. So this is a carb anion. Okay. So do you think it has a negative charge and it has all the electrons it wants? Do you think it wants more electrons around it? No. So do you think it wants to be stabilized by this methyl? No, because what does it stabilize it with? Electron density. So do I want more negative towards the negative? No. So what do you think the trend is here? Primary, then secondary, then tertiary. So for radical, and then I'm going to abbreviate it C+, meaning carbocation. Our trend is tertiary is the best, then secondary, then primary. And the reason is because these are electron deficient. Okay? Now, if I have a carb anion, what's the trend here? Which one's the best? Primary, then secondary, then tertiary. All right, and I think that's pretty much it for this chapter. We'll review this again on Monday.